Alright guys, so as part of the warm-up, this is going to kind of lead us into what the lesson is for today. So let's go ahead and check out some of these. So what we want to do is make a T-chart and graph each of the functions below. So let's go ahead and get to it. So a T-chart's always an XY. So we're just going to plug in values for X and see what we get out of it for Y, or for f of X in this particular case. So usually we want to plug in a couple negatives, so let's start with -2. So 2 to the -2 is 2 to the -2 is going to be 1 over 2 squared. So that's going to be 1 over 4. -1 is 2 to the -1, that's going to be 1 over 2, so that's 1/2. Plug in a 0 and you get 1. Anything to the 0 power is 1. Plug in a 1 here and you get 2. Plug in a 2 here and you get 4. Plug in a 3 here and you get 8. So that's probably enough to give us a general idea of what this graph looks like. So I'll plot my axes here. And let's go ahead and plot some points. So we've got -2. It's going to be right here, and we said it's just above the x-axis, so we're looking at 1/4 there. When we go to -1, it increases a little bit. 0 goes to 1. 2 goes to 4. I'm sorry, 1 goes to 2. 2 goes to 4. Looks something like this. And then at 3, we're going to jump up to 8. So our function, just generally, we're going to sketch this. Generally is going to look like this. And shoot up pretty quickly. Okay. Next one is 3 times 2 to the x. So pretty similar here. Our T-chart, again, we're going to plug in some values. We'll use the same values here. So we've got -2. If we plug in -2, it's really just going to be 3 times whatever we got over here. So 3 times 1/4 is 3/4. 3 times 1/2 is 3/2, or 1 1/2. 3 times 1 is going to be 3. When we plug in 1, we get 3 times 2 squared, which is 12. I'm sorry, 6. I said something wrong there. We're plugging in 1, so we get 3 times 2 to the 1. There we go. So 3 times 2 to the 1, that's 3 times 2, that's 6. Plug in a 2, you get 3 times 2 squared, that's 12. And then you plug in a 3, and you get 3 times 2 to the 3rd, which is 3 times 8. So we got 24. So I think we can sketch a general graph here. This thing is going to go up a little bit higher when we plug that in. But generally, again, we're plugging in the same points here. And our output, you can see, is a little bit greater. So we're at 3/4 instead of 1/4. 3/2 instead of 1/2. So let's say this is 1. So let's bring that down a little bit. Let's say this is 1. So our 3/4 is about right there. 3/2 is going to be about right there. 3 is going to be, there's 1, 2, 3. So here's 0, 3. 1, 2, 3. It's going to be up here. So 1, 6 is about right there. And then obviously we're going to shoot way up here on our next one. So this one, you can kind of see it increases a little bit quicker, and you can see what we did to the function. So relate the function to the graph is really what we're trying to do. And you can see the intercept here is at 3. The intercept here is at 1, and notice what your coefficient is there. So that's pretty interesting there. Either way, what I want you to look at is the base of this thing, the thing that's being raised to the exponent. They're both 2's, and notice what this graph is doing. They're both increasing. So we'll come back to that in a second. Let's do the same thing here, 0.5x. So let's make our T-chart. When you make the T-chart, you get x and a y. We're going to plug in some values. So -2, -1, 0, 1, 2, and 3. So 0.5 to the -2. That means you've got 1/2 to the -2. Negative tells me to flip, so I actually get 2 squared over 1 squared technically, but that's going to give me a 4. Same thing here. It's -1. It's 1/2 to the -1, so we flip it, so technically it is 2 to the first over 1. So that gives me a 2. 1/2 to the 0, anything to the 0 is a 1. 1/2 to the 1 is 1/2. 1/2 squared is going to be 1/2 times 1/2, so that's 1/4, and then 1/2 to the third is going to give me 1/8. So let's check out what's going on with this graph here. What's going on with this graph is basically as we plug in bigger numbers for x, so as we move to the right on the axis here, we're going to get smaller numbers for y. So what this thing is doing, we can see our intercept is at 0, 1. There's my point. At -2, it's at 4. So 1, 2, 3, 4. So it's about right there. At -1, it's at 2. And then as we increase to the right, so we plug in 1 and we get 1/2. We plug in 2 and we get 1/4. So we're decreasing even more. We plug in 3 and we get 1/8. So decreasing even more. So generally this thing is going to pass through these points. And we plot those points, and as we go further and further to the right, we're going to get closer and closer to that x-axis. Now, you can see these fractions are getting smaller and smaller, but what happens is we're going further and further to the right, but we're not necessarily going to ever get 0. We get closer and closer, but never get 0. Okay? Last graph here. Plug in your points here. And we plug in -2. And again, we're going to get 0.5 to the -2 is going to give us 4, but again, we're tacking on this 20, so that's going to be 20 times 4 is 80. Plug in a -1. I'm going to end up with 2 times 20 is 40. Plug in a 0, and you get 20. Plug in a 1, and you get 10. Plug in a 2, you get 20 times 1/4, which is 5. And plug in a 3, and you get 20 times 1/8, which is going to be 2.5, or 5/2. Okay, so we'll plot this. Let's go plot this, and this one's going to be a much greater graph. But essentially what happens here is, here's -1, here's -2. We're going to condense this graph a little bit. -2, we're up at 80, all the way up here, so let's call this 80. There's our point. Okay, at -1, we're at 40, so that's halfway down. At 0, we're at 20, so that's halfway. There's 20. Move over to 1, and we get halfway again. Move over to 2, and we get halfway. Move over to 3, and we get halfway, and so on. And so you can see this graph is much steeper. Much more steep. Okay, and it's still going to have that same behavior as we move, as we plug in bigger and bigger numbers for x. We're going to get closer and closer to the x-axis, or in other words, y is going to decrease. It's going to get closer and closer to 0. And again, I just want to bring up this fact that look at the thing that you are raising to the power. In this particular case, that thing is a fraction. It's a number less than 0. Up here, it was a number greater than 0. So that kind of takes us to what we're talking about here, our topic of conversation. And that topic of conversation is exponential functions. Okay, so any exponential function, an exponential function is any function that has a variable in the exponent. So you can think of a bunch of these ones. Obviously, we looked at some of them. So an example of that is y equals pi to the x. That's an exponential function. It might be kind of a weird looking exponential function, but it's an exponential function. Y equals 7 to the x. Or maybe 7 to the x plus 1. That's got a variable in the exponent. So that is an exponential function. Y equals e, this number e, this is just a constant, to the 3x pi. Exponential function, it's got a variable in the exponent. So the next thing we want to look at is we want to kind of characterize what these functions are. So we see some common themes between these functions. These two functions are increasing. These two functions are decreasing. So let's take a look at number one, what we call those. So exponential growth is essentially an exponential function that is increasing. So it's an increasing exponential function. All right, so if we look back, we've got these two functions are increasing. They're getting greater and greater. Our output, our f of x or our y, is getting greater and greater as x increases. So those are increasing exponential functions. So we would call these exponential growth, both of these. We go down here. These two functions are decreasing. So as we plug in greater and greater values for x, we're getting a decreasing function, or our output is decreasing from left to right. And so we would call these exponential decay. All right, so let me throw that little definition over here. So exponential decay is a decreasing exponential function. And so we're going to take a look at when are exponential functions decreasing and when are they increasing. So if we look back at these graphs, it'll give you a quick example. And if you remember back at the beginning, when we were originally looking at these, I kind of underlined what is the thing that's being raised to the power. The thing that's being raised to the power. So we've got these general exponential functions that kind of look like this. A general exponential function is going to look like f of x or y is equal to maybe some number times the base b, and that's the thing that's being raised to the power. Okay, so the b is the base. It's the thing being raised to the power. So if we're looking for exponential growth or exponential decay and trying to figure out what exactly this graph is going to look like, we're going to look at the base, and we're going to look at specifically what kind of number the base is. All right, so for exponential growth, we said the first two graphs were exponential growth. They generally increase from left to right, and they don't increase at the same rate. So for exponential growth, what you're going to see is you're going to see something where the base is less than 1. And when I say the base, I mean the absolute value of the base. So one example of this would be like 1/4. If we take 1/4 to some exponent, sorry, that's the other way around. This guy goes down here. That's decay. And we'll take a look at that in a second. So let's make sure we fix that. So this guy goes down here. And the reason being, for exponential growth, when we're taking a particular number, like for instance, when we raise 2 to a power, that number is going to get bigger and bigger as we go. So that's an example of exponential growth. So y equals 2 to the x, exponential growth. As we plug in bigger numbers for x, our output gets bigger and bigger. Another example would be y equals 7/2 to the x. That would be exponential growth. So you can see the general pattern is that we need the absolute value of b to be greater than 1 here. Or we need the base, or whatever we're raising to the exponent, to be greater than 1 in order to get exponential growth. All right? Down here, exponential decay is a decreasing exponential function. And that's the example that I accidentally gave before. So what we're looking at really is our base has got to be less than 1. It's got to be a fraction. We have to be raising a fraction to a power in order to get exponential decay. And just to remind you, exponential decay is going to look something like this. Some of them increase faster or decrease faster than others, but generally from left to right we're going to get a decreasing function. Alright guys, so the last thing we want to do is just take a look at a quick example here of an exponential function and the types of things that we can do with these. So you have 20 kilograms of plutonium lying around in your room, which might be semi-dangerous if you know anything about plutonium. If plutonium decays by 1% each year, we want to answer a couple different questions. The first question that we want to answer is we need to write a function that models this situation. And anytime it says write a function, you're going to have to identify some kind of pattern here. Okay? So if it's going to decay, that's number one. That means it's going to decrease. So it's going to look something like this. Our function will. By 1% each year, that means that we need to take the total amount and we need to kind of map out what's going on here. Okay, so after 1 year, what's going to happen is we start 20 kilograms. After 1 year, we're going to end up with something like this: 20 kilograms times 0.99, because it's going to decay by 1% each year. So we're going to start with our amount and we're going to multiply it by 0.99. And this is going to give us what we have after 1 year. Okay? So after 1 year. After 2 years. Well, essentially what's going to happen is we need to take the amount that we had here and then multiply it by 0.99 again. So we take what we had after 1 year, which is just 20 times 0.99, and we're going to multiply by 0.99 again. How about 3 years? So we check out 3 years. After 3 years, we take, again, it's going to decay by 1% the first year, and then whatever you have left after the first year, you're going to take, it's going to decay by another 1%, and then the third year, you need to take what you had after the second year, which is 20 times 0.99 times 0.99, and multiply by another 0.99, or take 99% of that. So hopefully you can kind of see the pattern here, and we can simplify these things. Here we have 20 times 0.99 to the first. Here we've got 20 times 0.99, and we're multiplying 2 of them, so that's to the second power. Here we've got 20 times 0.99, and we're multiplying 3 of them, so that's to the third power, and so on. And so the point here is that if we want to write a function that models this, the exponents are actually the years, or the amount of time that's passing in years. So if we're going to write a function that models this situation, it's going to be the initial amount, the rate of decay, and we're going to raise that to however many years have passed by. And so we'll denote t in time. All right, so y in this particular case is the amount of plutonium remaining after t years. That's what our function is modeling. Okay? So we can go down here and figure out how much plutonium remains after 10 years. We don't have to continue to do this individually for year 4 and 5 and 6 and 7 and 8 and 9 and 10 all the way up. All we need to do is y equals 20 times our rate of decay. And again, this is less than 1, which means it is decreasing. And we want to know after 10 years, so we're going to raise that to the 10th power. All right, so plug that into your calculator, and yes, that's a nice thing, is you do get to use your calculators for this portion. Plug that into your calculator and you get about 18.09, and that's in kilograms of plutonium remaining after 10 years. All right, so these exponential functions, number one, we have rate of decay and rate of growth. And to put that another way, we've got, remember, we have exponential growth or exponential decay, depending on what that function is going to do. And then we can use these exponential functions to model that exponential growth or exponential decay in particular situations like this. So remember, this is your rate. Whatever is being raised to the power is going to be your rate of growth or your rate of decay. This is going to be the initial amount of whatever you have. And your function y, or f of x, or whatever you label that, is going to be the amount remaining after a particular amount of years in this particular case.